So the idea which surfaced already quite a number of years ago, and which was pursued by us and by other groups, and especially by Jim Stanley, was that what about thinking in the same terms, not only about systems which are made of molecules, but systems which are made of individuals or of individual companies or many other, so to speak, microscopic systems. And the outcome of it is not only that this kind of dramatic what is called phase transition between liquid and gas, not only that they do happen in economic systems and in social systems, but they happen even more energetically because of this feedback between the macroscopic situation and the microscopic one. Like in the water, the fact that some water molecule at the other end of the system is now liberating itself from the bonds and evaporating. It's not influencing directly another molecule which is at the other side of the system. However, in the case of economics, because the agents, the microscopic, so to speak, agents are humans, they do communicate, they do see TV, they do have a government which, or a central bank which can change the interest rate for all of them as a result of some of them going bankrupt. And because of this, the effects are not smaller, but they are, in fact, stronger. And this graph was actually, it's a very old slide, because you see I have the example of 87 and the example of 29, but I don't have the example of 2008 because the slide, it's older than 2008. But definitely, in a sense, it shows that it was a very good point to try to understand these things. And maybe if we would have put more pressure on ourselves, we would have said something intelligent about 2008 before the 2008 happened. Like, for instance, the kind of comment which we had before about what can happen. So what is interesting about what I said until now is that I didn't enter at all in the chemistry of the water molecules. I didn't tell you how the hydrogen inside the water molecule connects to the oxygen, and it is not even important. What is important is this kind of connections between the molecules. It's a rather geometric point of view about what happens with the clusters rather than what happens with the details of the chemistry. And this is why the same method which can be applied or many of the methods which can be applied to these physical systems can be applied also to other systems, because the phenomena which happen are not always related with the details of the properties of the microscopic objects, but rather with the kind of structures that the microscopic objects generate. So this kind of a program was initiated quite a number of years ago. It's usually associated with Phil Anderson, and I mentioned to you in the beginning of the course about this idea of more is different, and it can be applied, as I mentioned from the beginning, it can be applied to chemicals which are connected by reactions or by chemical bonds, and but they can generate at the macroscopic level something which is qualitatively different, something like metabolism. On the other hand, so you get from non-alive system to alive system by considering this kind of collective phenomena. And the same kind of situation can happen inside the living bodies, having very simple molecules, which when they are put together, they can lead to systems which are behaving very intelligently. Like neurons producing as a collective system something like knowledge, or the antibodies in the immune system also producing some kind of cognitive output, which is essentially identifying what is self and what is not self, and trying to eliminate the non-self from the organism. And the same kind of scheme can be applied to systems in which the links are very different and the nodes are very different. So this kind of point of view in which you think about a system as made out of many individual entities, microscopic individual identities, it's quite universal, and it can be applied to very many systems. In particular, for instance, you, at the time that this slide was, it's again a very old slide, in more than 15 years ago, the first wave, now we have waves almost every 2 months. There is something like Candy Crush or WhatsApp, or this kind of viral adoption of a new convention, of a new technological innovation. But among the first ones which took place was the Tamagotchi craze. There was a kind of Tamagotchi in Japanese means watch and pet. So it was like a little clock, a little watch, and it had a pet which you had to entertain and to give food and things like that. And it had at the time it was a very singular occurrence. Now we see it happening every day, but at the time it was very crazy that something which is does not have an obvious use, is not like food or education. It had a very, very fast adoption rate. There were sometimes people were sitting in a line in a new country which was importing Tamagotchi. They would stand in lines for 2 days to buy one. And but it also had a collapse. In the next year, the producers produced more of this. But in the meantime, the market was saturated, and in fact, they ended with a loss. So this kind of very dramatic phenomena started to happen quite a number of years ago, and now they became the steady state of the economy. So we are now in a situation in which the exceptional becomes the rule. And this is, as you remember, some of the quotations from Phil Anderson. He said it again quite a number of years ago. And the same kind of phenomena can be applied to the way the innovators are influencing one another, the way the firms are influencing their states. And this is the kind of things which I'm going to discuss in this lecture. It's basically based on a model which was proposed in the year 2000. And again, when it was invented, it was about, especially about adoption of movies. The thing which at that time, it started to, in Hollywood, they started to have this kind of big hits movies, in which, and sometimes having even a series of them. And it wasn't obvious from the beginning why a certain movie would succeed and another movie would not succeed. Even though they looked similar, they had similar cast, they had similar plots. So we wanted to understand this hits and flop phenomenon, And it is, as you will see already during this lecture, and maybe more in the coming lectures, this kind of systems which I'm going to discuss now, they are capable of starting from the premises that the entire system is not uniform, but it's made out of individual microscopic elements. You can start to understand why you have hits and flops for movies, or why you have innovations which can lead to cascades which completely change the technology and the economy throughout an entire country or throughout the entire world, and things like that. And of course also diseases. This is a very partial list of the kind of I call it nodes and links because in a short while you'll see that the way, one of the ways to visualize it is to think about some kind of a network in which the different microscopic individuals are nodes, and their interaction is symbolized by connections. And of course, just two nodes connected by a connection doesn't mean very much, but when you have many of them connected together, then already you can start having structures which are very non-trivial, which have very interesting properties, and which in the end can explain this kind of very dramatic events which I was mentioning before in terms of economic crashes or technological cascades, or health hazards in terms of epidemics and things like that. It, however, I should say, especially in a course that is addressed to social and human sciences, that this also happens to ideas and concepts and religions and philosophical systems. So, here is again the analog of what global view of the system can lead, and what a microscopic view of the system can say. This is a graph of adoption of cars, basically from the moment that the cars were invented. And at the beginning, you see there is a kind of exponential growth from basically 0 to thousands of cars. And you might think that given this, the simplest theory, which essentially says that the number of adopters is proportional, at a given time it's proportional with how many adopted already times how many didn't adopt, and therefore they are likely to adopt. So some very naive global estimation. And then you get this kind of a curve. At the beginning, it's exponential, and at some stage, you exhaust your market. In reality, actually, this was not at all like this. As you see, there are very large fluctuations. And in fact, even these fluctuations are very misleading, because we are speaking about thousands of sales, while nowadays the sales of cars in the world are many orders of magnitude higher. So this kind of naive estimation is not very appropriate, and rather I will present now in some detail a model which explains how this kind of propagation of sales or of ideas or of crisis can take place essentially by contagion. And of course, the mere concept of contagion is known to everybody, and it doesn't. I don't have to make a lot of effort to make you agree or accept it. But what you'll see that this very simple concept of contagion can lead to very, very dramatic changes in the regime of the system. For instance, it can lead to a situation in which below a certain value of the parameters of the external conditions of the system, the contagion doesn't lead to the adoption or to the thickness of many people. It can be very, very limited, and very small, sometimes a very small change in the state of even a microscopic participant can trigger a macroscopic avalanche which would affect the entire system. So this is a thing which we are going to see how it can happen. So for the moment, I'm just defining the model. Suppose that I represent the different I represent the different microscopic agents by this kind of little squares or little circles, and the squares are non-adopters, let's say not susceptible of getting the disease, and the blue ones are susceptible of getting the disease, and this, which was supposed to be black, but we have very severe problems with the color, so I guess it's seen as green here. This one represents a susceptible one, which not only was susceptible, but in fact now he is sick. As I said, there are so many applications that it sometimes I have a tendency to mix between saying that this is a sick guy, which is, and these are susceptible patients, or that this is a person which has bought an air conditioner, and therefore his neighbors are likely to buy air conditioners if they have the money, or these ones are not likely. And things. So for the moment, just for definiteness, I will speak in terms of product which is bought or not bought by these individuals. So if this individual has bought this product, you can imagine that his name, that he speaks, or this object is seen only by its neighbors, and therefore the neighbors which are likely to buy, they will also buy. The one which, let's say, is allergic to air conditioning or doesn't have the money, he will not buy. Moreover, the more distant neighbors will, until they are reached by the knowledge about this product, they will not buy. So now the question is, what would be the propagation of buying of air conditioners in this kind of society? Of course, this is highly non-realistic. I take that each individual has 4 neighbors. It can happen in an example which we had in another lecture, in which they were living in a suburban neighborhood in which everybody has a house and 2 houses on each, 1 house on each side and 1 in front of him. But in general, this is not the case. But what I'm going to say is much more general than this planar scheme. So what is to be noticed on this scheme? You see, the blue circles are the potential buyers. And if somebody would be a producer of air conditioners and will send people to scout around and to ask people whether they are likely to buy something which looks like air conditioning, then he will be very happy, because you see there is more than half of the nodes. Huh? Yes. So, if you are a naive producer, you'll friction your hand and say, "Wow, this is a very great opportunity for business." However, according to our rules, of course, you can try to make a lot of advertisement, and it might work. However, especially for things which are not experienced directly, advertisements don't necessarily work. You need really to go to the neighbor, sit for 5 minutes there, see that even though it's very hot outside, it's very pleasant in his house, and then you will buy. So, so if you assume that this is the case, then essentially you will see that the adoption will be actually quite limited. Why is it so? You see, suppose on what did I do here? I made connections between all the adopters, potential adopters, which are in the system. And then you see that they are now clustered in separate clusters. This guy is not a direct neighbor of this guy. Therefore, there is no link between them. So if you make the links, you realize that now that the system is actually fractionalized in between different clusters. So even though you have more than 50% adopters, if you start, suppose that you give an air conditioner for free to some person, or that he was on vacation to his grandmother and he thought that air conditioners are good, and then he buys it. Then by the mechanism of contagion, which we just said, this one will buy too, because he's a blue circle. I already took out the squares because they are irrelevant anyway. They don't buy, and therefore they don't transmit, and they are not there. So according to the rules, if this bought, then this neighbor of his will buy too. And if this bought, this one has two neighbors which are susceptible of buying air conditioning, they will buy too. And those neighbors of theirs, they will buy too. But this is it. The avalanche of buying will stop here, because there is no additional neighbor which is likely to buy. So, the air conditioner producer, which would have taken the chance of producing as many air conditioners as to provide to half of the population, will really go bankrupt. Out of the, maybe this lattice was much larger, but in the end, all he got was 2, 4, 6, 7 air conditioners out of maybe 100 or 1,000. I don't know. Depends on how large is the system. So this would be a very dramatic event for him. Now, suppose, however, that he is lowering a little bit the price of the air conditioner, and he transforms this guy, which used to be a rejector because he didn't have enough money, or he didn't think that for that money it's worth. Suppose that he becomes an adopter. Then, since he's in contact with this, he will, in fact, will buy. But not only he will buy, his very presence will make the contact between these clusters which were separated, and therefore the entire process will now be able to continue for quite a while before being stopped again. So you see, it is still true that some of the potential buyers are not reached by the propagation of the campaign, of the selling campaign. However, they are much more than 15%. Now they are a very large portion of the potential market. And you might, now they are 22 out of 27. But of course you can say, well, I arranged in advance such that just a small change in the price, which would just convince one single microscopic element, would have such a macroscopic event. And in fact, I did choose this example by hand. However, it represents a real phenomenon. And this one, for instance, the adopters were not chosen by hand. These black crosses are the potential adopters, and the empty sides are not are rejectors. And the density of potential adopters throughout this entire area was 55%, like before. More than half of the sites were ready to adopt, to buy an air conditioner, for instance, if only they were exposed to it by one of their neighbors having one. And still, this cluster, which was conquered by the air conditioner seller, is, as you see, very limited. There were, and this is not by lack of potential buyers. The system is full of potential buyers. It's just that they are not in contact with the ones which already were adopting. So there is now, we are making now a very strong differentiation between potential adopters, the size of your potential market, and the actual sales, which can be two very different things. And now we also understand what is wrong with the colors. This had a certain color which is apparently completely missing in the computer rendering. So how this could change? As I said, these points were chosen randomly, really by some random generator on the computer. So now suppose that, that you are passing from 55%, one adds just 5% more adopters. And they happen to be these green squares here. The new sites which used to be non-adopters, and now they are made adopters, maybe by lowering the price or by maybe making some improvement in the air conditioner. Maybe making some long-distance controls on it, or making the engine more powerful. Now, these 5% are now going to make a hell of a difference, because you see that now, because of this one, this initial cluster, which was conquered anyway, is going to be in contact with this cluster, which is going to be conquered too by the air conditioner. And once this one is conquered, then because of this new adopter, which wasn't there before, this cluster is going to be taken too. And now, because this one has adopted, this site will make the contact to the next cluster. And now there is this one, this cluster, which is also conquered. And then because of this site, this one is also conquered. And so on. You see that the additional 5%, with this time, as opposed to the situation in which I put by hand a new one, in this case, a random change of only 5% in the potential number density of buyers leads to a very macroscopic effect. In fact, you see that the region which I have shown until now is part of a much larger lattice, which eventually was conquered once you went from 55% to 60% potential adopters. So this is called the percolation transition. You see, if you wouldn't have this limited connections between the participants, and if everybody would know perfectly everything which happens in the system, which is actually the usual assumption in economic systems, perfect knowledge of every one of the participants, then if you made a graph which relates the density of potential adopters to the density of actual adopters, then you would have a straight line. Whoever was a potential adopter, he will actually adopt. However, the situation which we are discovering here is very, very different. For a very long while, it is essentially 0%, very close to 0% adopters, and only when the density gets to some critical density, you start having a significant fraction of the microscopic agents adopting and being part of this avalanche of adoption. So in place of having this kind of straight line, you have this very special line, which incidentally for small systems like this, in which you have, let's say, 100, 1,000 participants, these are still the transition from the non-adopting phase to the adopting phase. It's relatively smooth. However, as you go to larger and larger systems, like for instance we have in the world, we have hundreds of millions of viewers of a movie. In this case, one gets closer and closer to a situation in which up to that critical density, there is essentially 0% of adopters. There might be hundreds of people, but hundreds of people compared with a market of 1 billion, of 100 million people which in principle could go to see that movie, it's negligible, so it's 0%. And only at this particular density, you have a very dramatic increase in the number of actual adopters, of actual goers to that movie, let's say, or to buying air conditioning. So this phase transition is very significant. It's quite dramatic, and as I said, even more important than that, it's very general. This kind of change in the behavior of the system upon a very small change in the parameters in the system is the kind of things which happen nowadays very often. So this is actually, and I hope that the movie is working. So as I said, for large enough systems, actually the graph looks very dramatic. You have 0% adoption up to certain density, and then out of a sudden everybody starts adopting. In terms of time, this is a logarithmic scale. You have essentially nothing. Then exactly at the critical value, you have a very, very fluctuating schedule of sales. And for larger values, you have essentially an exponential increase, because this is a logarithmic scale. So straight line here means exponential. It's still very fluctuating, but exponential. Now, let me see if the movie is working. If not, I will get for a moment out of the... Let me get for a moment out of this and put the movie. So this is essentially a movie of what you saw before. The colors are again not the right colors because of the computer. And this is a run in which is just a little bit above the phase transition. You see, basically the entire system is conquered. The different campaigns, they are essentially joining one another and filling almost the entire system. However, there is another example which is much closer to this critical value of the density, and which you will see that even though it still conquers a very large part of the lattice, it leaves a relatively large. No. It's also conquering the entire lattice. But of course, there are examples in which this is not the case, and only a part of the lattice is conquered. These are some more examples of how this happens, because suppose that I'm slowly increasing the number of potential adopters. Then if I started with a relatively low density, you see that I colored the clusters with different colors. So this was a cluster, and this was a cluster, and this was a cluster, and this was a cluster. And by just increasing the number of potential adapters by a very small density, which essentially concretized in this case in these three new links, these links were, nodes. These nodes were enough to connect these four different former clusters and make a cluster which is much, much larger. So this explains, you see, the growth of the clusters is not like an onion that you add another one more shell on it, but it's essentially each cluster, once you increase the density of adopters, it meets other clusters which are more or less of the same size with him, and therefore essentially, so to speak, doubling or tripling its size. So this is why you have this kind of very fast increase of the size of the cluster as you approach the critical density. So this is another example, and this already you see that the cluster, there were two clusters, the blue one and the black one. The boundary conditions were periodic, so this black one is the same with the black one here, and there was enough that there is one more side here to connect both of them and to transform the entire system into a system which has a very large cluster. And what happens is that when you make a little movie of it, you see, the movie does the following. It shows which are the new sites which were added, and the resulting clusters which they produced. And on this graph, one just plots the number of nodes which exist in the largest cluster. So essentially, you have on the left side of the graph, you have the history of the growth of the amount of adopters. And here you have a graph which says how does the number of adopters depend on the density of adopters which we have. And as you saw before, on this kind of, on this particular lattice, one has the critical density is around 59. So you will see that indeed the curve, this curve which plots how many adopters I have as a function of the density, will essentially try to diverge here. Of course, it's not really diverge to infinity because the system is not infinitely large, but it will still have a very, you'll see that it approximates very well this statement. So you see this cluster starts to be formed. And, but then the other one, it's uniting and therefore becomes the largest. And then it grows. And now we are in this. This is the same run which I showed before, just animated. So this is the blue one, and there is the black one, and there is this one which you just joined the blue one. And now in the next step, the black and the blue have joined because somebody here has adopted. Yeah, you see here. So, and when I count the volume of the largest cluster, you see that I get these numbers which are very much falling on a line, which is the theoretical line. And there is a problem also, I see, with the characters here. But essentially, we have this formula probably later. I will show it. So the point is that I'm not going to show exactly. Actually, maybe I'm going to show how to characterize, how to understand this line in quantitative ways. I promise there will be no more mathematics in the course. So if you, it will take less than 5 minutes, and you can even ignore. But before that, I want to make the point that if this is the price of the air conditioners, and this is the number of air conditioners which were bought. And now the point is that if I start with a very high price, then there will be very few guys which buy it. And of course, still, if this one bought, and if these guys which are here, they are willing to pay prices which are higher than this one, they will also buy. So for a while, if this one bought, then there will be an entire little area of his neighbors which will buy too. But at some stage, there will be somebody which is willing to pay only this price, and therefore the entire expansion of this area is stopping. However, if I further lower the price such that this guy will buy, then all these others here, they are willing to pay higher prices, and therefore they will buy too. So the campaign, I can imagine that it could go like this, that each time I get stuck, I lower the price, and then I conquer yet another territory of all the neighbors of this guy, which are willing to pay more than himself, than the guy which, than the individual which blocked my advancement. Is it clear? Is it clear what I? So why am I insisting on that? Because essentially, this line, which connects all these guys which were blocking and for which I had to lower the price, is essentially the same line which tells me what is the density of potential adopters, which is necessary for the largest cluster to have a certain size. So n depends on p, but actually depends on the density of potential adopters. Okay, so here the formula appears better. So there is a little formula which even though I said we don't want mathematics, it's nice because it connects instead of having a situation which is in the absence of this kind of network effects, instead of having a situation in which n would be just the density times the total number, so n and rho would be completely proportional. Now we have a very special situation in which, in fact, when rho reaches the critical rho, you have 1 minus 1 is 0 to some negative value, which means the n goes to infinity. But before that, it's finite. So infinity, it means the entire system, if the system is finite. So this formula is important because it encapsulates all these words, which I was saying for quite a while, and some of them maybe they were informative, but some of them they were maybe just some comments which we could have passed. This formula has the quality of saying in a very quantitative way, you give me what is the density of potential adopters, you give me the geometry of the system, and I tell you when you expect to have this kind of divergent cascade, and therefore when the system is in danger. Well, if it is a negative thing, then it's in danger. If it is a positive, is what is the price for air conditioners for which you are going to make a lot of profit? It's paradoxical, but of course well known by sellers that if you lower the price, then you might actually make a much better profit, because if you have a high price and nobody buys, then you don't make any profit. If you lower the price and then you conquer the entire market, then you make profit. So the right way to make a profit, and maybe this would be good for, in this country, we always have, in the last years, problems with consumer goods being too expensive. This shows that a producer or a seller can make a very good profit. In fact, better if one keeps the prices lower. So this has been checked by one of the scientists at this university. He made his PhD some years ago with me, but now he's applying it and having great success in applying these ideas to marketing, and in particular this criterion of whether when you check the space and time distribution of the sales, whether you can get a signal whether the campaign will succeed or not. Because if you get some scattered points which are not related to one another, then the sign is that they bought because they saw some commercial, but they didn't recommend to their neighbors, and therefore you don't expect the product to succeed. But if you see that the sales are clustered among different neighborhoods, then you know that this was not due just to everybody seeing the TV and some of them buying randomly, but this was due to the fact that this product has some kind of viral appeal, either because it's very good or maybe some other reasons, but definitely it's going to succeed. So you have a criterion for deciding very early in a campaign whether the campaign is going to succeed or not. So it's very similar indeed to what we had. And now I'm going to make this little computation which would explain in a quantitative way, it will explain in a quantitative way the propagation, why you have this kind of divergent function. We are going to deduce in this particular case, which I'm describing now, the this function which connects the density of potential adopters with the number of actual adopters, and shows that for a certain critical density of potential adopters, you actually get an infinity of actual adopters, or at least a very large part of the system if the system is finite. So in order to make the computation really simple and in fact similar to the computation, this is why I'm giving it, because it's mathematically it's very similar with the computation which we made already. You'll see, you'll recognize some formula which we already deduced. So now, again, we are imagining that these circles are individuals, are microscopic individuals, and we are assuming for simplicity that each of them has just 3 neighbors, or k neighbors. In this case, there are 3, but we'll say that it has k neighbors, okay? Except this one, his neighbor, we don't see it. This is the guy from which the entire campaign will start. And now we are also assuming that there is a certain density of susceptible microscopic agents. In this case, it's not in terms of buying air conditionings, but it's in terms of companies which are essentially endangered. They are not. They cannot pay really their loans, but they hide it, and therefore they will be discovered only if one of their neighbors is already bankrupt. Then people will start looking into the accounts of the partners of that company which went bankrupt, and discover that they are also essentially bankrupt, and they will be treated as bankrupt. So we have this, they were supposed to be red, but I see that they are orange on this screen. And therefore, if you have, for instance, if you assume that this company went bankrupt, maybe because some neighbor from here went bankrupt, then this company will not go bankrupt because it is a healthy company, and even upon scrutiny will came out okay. But this one will actually be contaminated and will become bankrupt too. So now, assuming that I have a certain density of such companies, and that each company has k neighbors, we can ask how many, if I have one company which went bankrupt, how many companies do I expect to go bankrupt following this bankruptcy, okay? So the company has k neighbors. So k neighbor, more than k companies couldn't get in the first stage contaminated because only k of them are neighbors. But out of this k, many of them are not susceptible. They are not endangered. How many are they endangered? A density rho of them, a fraction rho of them. So how many of these companies, of these k companies, will actually go bankrupt? Rho times k. Actually, it's rho times k minus 1, because one of the neighbors is the neighbors which contaminated this guy. So there are only k minus 1 left, which are the...
Do we have to know this math?
Hmm?
Do we have to know this math? Because you did say there would be no more math.
Say it again?
Do we have to know this math?
You will not have to know that, but I would be very happy if I would succeed to make you understand it. Let's take this example, okay? There is this guy here. He has 3 neighbors, but this one is already contaminated. This is how he got contaminated. So now he has 2 neighbors, okay? Yes? Now, suppose that I have the probability half that one of them is susceptible and the other one is not, okay? Then how many will get contaminated? 1. Out of 2, half is 1. If there will be 4 out of, and the density of susceptible one would be half, it would be 4 times half, 2. So this is what this formula says. It's k, but k minus 1, because one of them is not there. So in place of 2, it's k. In place of this 2, it's 3 minus 1, it's k minus 1, okay? Times the probability that that each of them is susceptible, okay? So I have the probability of somebody being susceptible times the number of neighbors which this guy has.
So K is the number of neighbors?
Yes. K was
Just the number of
each of the guys have, in my case, here has 3 neighbors. But in general, suppose that there were K. Okay? In our case, K minus 1 is 2 on this scheme. Yes?
On this scheme, every K equals to 2, basically?
Yes. This is what, you see, I take a very special scheme such that I can have the hope that still to make it understood the formula. In general, that formula that I gave is more complicated, but this one, in these conditions, I hope is very easy to understand. So each node has K neighbors. In this K, in this drawing, K is equal to 3. 1, 2, 3. This is a neighbor, this is a neighbor, this is a neighbor. This is a neighbor, this is a neighbor, this is a neighbor. This is a neighbor, this is a neighbor, this is a neighbor. This one, I'm not showing the third neighbor because it's the neighbor from which he got contaminated. So now the question is how many of the other ones, K minus 1, are going to be contaminated? And if you tell me what is the fraction of contaminatable guys in the system, then the number of contaminated, which I expect, it is K minus 1, the neighbors which are left of this one, times that fraction of contaminated people.
And if I'm not being given the fraction, how can I?
If you don't know the fraction, then let's, I mean, right now we are discussing this problem and trying to get a formula. After that, you can get the fraction because if you are looking at the propagation of the system long enough, then you see how many they are contaminated at each step. So you will be able to evaluate. Meantime, I'm trying to solve this problem. And did you? Okay. So now, after I contaminated the first one, so I'm now counting how many contaminations I have during this process. So I have first one, and after the first one, there are his left K minus 1 neighbors, out of which only K minus 1 times rho are going to be contaminated. Now I'm asking you, what is going to be the next wave of contaminations? I have now K minus 1 times rho sites. Each of them have K minus 1 new neighbors. And out of these neighbors, fraction rho will also actually get contaminated. So for each of these guys, I will have K minus 1 times rho, which he will contaminate. Exactly like what happened to him is going to happen to this guy. This one is already contaminated, but out of his 2 neighbors, one of them will get contaminated. So in general, I will have a situation in which the next generation would be K minus 1 rho times K minus 1 rho being contaminated. Now you can guess what is the next generation.
Times 4, like in the power of 4?
No, in the power of 3. So because I have, this is the number of guys which are now actively have been contaminated. Each of them has K minus 1 neighbors. Out of these neighbors, a fraction rho is going to be really contaminated because the others are not susceptible. So in general, I have a series like this. Now, you understand why I really insisted, in spite of my effort not to give mathematics, I'm actually giving this series. Do you remember this series? We had it many times. 1 plus x squared plus x third plus x to the n. Do you remember how much it was? It was 1 minus x to the n over 1 minus x, roughly. Okay? But you don't have to remember that, as I said, and it's not going to be in the exam. What we can do is the following. What we can do is the following. Suppose that rho it's exactly 1 over k minus 1. Okay? It could be more or it could be less, yes? Hmm? But if it is exactly equal to that, then each of these terms is going to be equal to 1. Yes? If k minus 1 times rho is 1, then this is 1, and this is 1 squared is 1, and this is 1/3 is 1, and so on. So as time passes, as I have a new generation of adopters, I am adding one more adopter each time. So the number of failed companies, if I'm speaking about companies, or the number of sales, if I'm speaking about sales, will increase linearly with the number of generations of contagion. If it is if k minus 1 times rho is larger than 1, then of course you will have, suppose that it's 2. Then this is 1 plus 2 plus 4 plus 8 plus and so on. It will increase exponentially. So this is why I have chosen this case as the initial case. This is the limit case. This is a case which makes the boundary, the separation between the situation in which this process is going to saturate, because you have smaller and smaller expectation of contagions to take place, when the density is less than k minus 1, and therefore k minus 1 times rho is less than 1, this is a convergence series. While this is for k minus 1 times rho larger than 1, this is a divergent series, and it diverges exponentially. This is a breaking point. This is a critical value. Below that value, if I start a propagation, if I start a campaign, the campaign will be bogged down, will not succeed. Exactly at this value, it will be unsure. Every little thing can change the situation. If I expect that each generation will have one adoption, but if I'm unlucky and it doesn't have any adoption, then the entire thing stopped. Here it's not like this. Here, even if there is some generation which has some misses, out of 8 or 16, which I expect, if there are 15 or 14 or even 10, is not such a disaster. The next time I will be luckier. So still, the campaign is going to succeed. So now is the time to remember this formula. When n plus x squared and so on, for x less than 1, it's 1 over 1 minus x. That was a formula which we did use before. Again, if you don't want, you don't have to remember. But I do remember it, and I do realize that therefore, therefore the number of failed companies as a function of the number of neighbors of each company, of partners, and as a function of susceptible companies, is given by 1 minus rho k minus 1 to the minus 1. What does it mean? It means that when rho gets closer and closer to 1 over k minus 1, the number of failed companies will go to infinity. I should be careful. And this is, of course, the question which you ask. Of course, you can ask not only, do I know rho? You can ask, do I know really how many partners each company has? Well, it depends. In a work which I mentioned in the past with Professor Golo, we did get a lot of information from the largest bank conglomerate. And also there is the group in Ireland, which also has this kind of data, in which you can have some information about the structure of the network. Of course, the network is not exactly with exactly k neighbors, but you can know how many partners a company has. Again, if you have somebody to entrust you with the data. So the point is that if I know what is the average density of susceptible companies, and what is the structure of the trade network between them, then I can tell the responsible for the regulators of that system, I can tell them, look, you are very close to the critical value. If you are increasing just if you are allowing just a little bit the number of Ponzi companies, the companies which are which are essentially not capable of paying their interest rate, their interest. If you are increasing just a little bit, then it's going to be a disaster. Now, and of course, then their reaction shouldn't be, it's like this, we have too many loans, let's increase the interest rate, because this only increase will give the last push. And actually, in some of the books which made the history of the crisis, not only in the distant past, but even in the recent ones, it turns out that indeed, in most of the cases, it was this intervention by the regulators which started to realize that there is a problem, which in fact instead of delaying the collapse, in fact, this was the last act which actually triggered the entire collapse. And I think that I can stop here. In the next lecture, we'll see what happens when you have more. This is actually how I started to present this importance of networks. We'll see in the next lecture what happens if you have the interactions between the different networks. In this case, you have the interaction between the expectations, the economic expectations of people, let's say, they influence one another, let's say, by having discussion at their working place about what is the future business, and between their propensity to save or to spend, which is influenced by looking at their neighbors, whether they bought an air conditioning or not. So now we are going to discuss not just one network, let's say the propagation of adoption of a product within the network of customers, but also connect the different networks which are influencing the same individuals, and see that in the same way in which we had very unexpected and very dramatic effects coming from this microscopic view of the propagation of crisis or of sales, we will have very special effects coming from the interactions of the different networks. We are finished for today.